So today we're going to get into the fundamental theorem of calculus. For the most part, you've been introduced to both major branches of calculus: differential calc, which is finding the slope of your tangent line, and integral calc, which is finding area underneath the curve. These were both discovered by Isaac Newton and by Leibniz in about the same time, and both of their ideas were incorporated into the fundamental theorem of calculus. Basically, it comes down to this, that differential calculus and integration are inverse operations. They undo each other, just like multiplication and division or addition and subtraction. So we were dealing with, in the first section of this chapter, an anti-differentiation, so an indefinite integral. And then there's the definite integral over here on the right. Definite integral over here has bounds on your integral. So an indefinite integral is finding some function, and that will give you the same derivative. So you have to have plus c, because your function could be moved up and down at all, and it would not affect your original derivative. So that's what that plus c does, is move a function up and down. Where a definite integral is just representing the area underneath your curve. And for the most part, it comes down to you integrate f to get capital F, and then you evaluate it. So capital F is your antiderivative, is for the most part what it boils down to. And that's what we're saying here. If lowercase f is a continuous function in a closed interval, capital F is the antiderivative. So to evaluate this, you find your antiderivative of lowercase f to get capital F, and then evaluate it from b to a. So you plug in b into capital F minus what you get when you plug in a. That allows you to be able to find the exact area underneath function lowercase f. Now you might be wondering, why don't we have to put plus c in there? Well, we could. If we integrated this and evaluated it, included plus c, we'd have to put f or b into capital F, so we'd have f of b with a plus c minus what we get when we plug in a, which would be capital F of a with a plus c. But if you get rid of the brackets here, because they're not doing anything, and you distribute through the negative here, you'd have a plus c and a minus c, so the c's would drop. So on a definite integral, you don't need to have plus c. On an indefinite integral, one without the bounds, you must have a plus c. So let's go ahead and evaluate this. Now remember, this means we want to find the area underneath our curve of x squared from 0 to 3. Now we did this the other day using the limit process. But based on what we've just learned, we should be able to do our integration of this, our indefinite integral. So increase your exponent by 1, and then you'd have to have a 1/3 in front to offset that exponent. And then evaluate it from 3 to 0. So take 3, plug it in here, minus what you get when you plug in 0. So in this case, we end up getting 9. And that's what we got before. However, most people find what we just did here a lot easier than doing that whole limit process with the summation notation and all that. So here, if we're looking for the area underneath our sine curve from 0 to pi, which is graphed out down below here, you have to integrate sine. You got to think, okay, the derivative of what is sine? And well, that's a negative cosine. Evaluate it from pi to 0, so you plug in pi minus what you get when you plug in 0. Cosine of pi, you know, is -1. Take the opposite of that is 1. Cosine of 0, you know, is 1. Minus and minus is really a +1. In other words, you get 2. Which is somewhat interesting. You're dealing with a trig function, you're dealing with an irrational number, and you're finding your area underneath sine between 0 and pi, which is an irrational number, and it comes out to be a nice, neat, normal, natural number. So here, we have 3 terms that are added and subtracted. If you were to look at the graph, it would be similar to this one down here. It's not a straight line. It's somewhat close to a straight line, but it's not. If you're looking for your area, you'd have to integrate each piece, increase your exponent by 1. Remember, you got to then put the reciprocal of that in front to offset it. And then you'd have this evaluated from 9 to 1. So you take 9, plug it in for all your x's, minus what you get when you plug in 1 for all your x's. Now you could work it out all by hand, but I think if I were you, I would go ahead and take this line right here, type it in all at once into my calculator just as I see it, so therefore I'm not making any mental mistakes. So next one, you can see your graph down below here, what it looks like, and we're looking for that area because it's a definite integral. So we'd have to increase our exponent by 1, so that would be a 4. But then remember, we'd have to have something in front to offset that, so we'd have a 1 over 4. But then also remember, we have to undo our chain rule. The derivative of the inside is 2, so you'd have to have a 1/2 hanging out here, and then evaluate it from 1 to 0. Well, our 1/2 and our 1/4 really gives us a 1/8. So now all we have to do is plug in 1 minus what we get when we plug in 0. Some problems like this are pretty easy to do in your head. If you did want to go ahead and just type in this whole line into your calculator all at once, that would be perfectly fine. In either case, you end up getting 10. So here, our area is being displayed over here on the lower right. We're looking for the area underneath this function from 1 to 5. Well, remember, this is an exponent of 1/2, so you'd have to increase your exponent by 1. So we'd have to have a 2/3 in front to undo that exponent. Then once again, we'd also have to have something to undo our chain rule. The derivative of the inside is 3, so we'd have to have a 1/3 hanging out. Then we can evaluate it. Now, that 1/3 and our 2/3 gives us really a 2/9 in front. Then plug in your 5 minus what you get when you plug in 1. And then once again, this whole line, I would maybe just type into my calculator all at once, or you can do it in your head. It does not make a difference. Now, if it does not come out to be a nice, neat number, or a number that can be written as a fraction, you're going to have to work it out by hand. You will come across some problems where there'll be roots in your answer, or logs of a number in your answer, so therefore you'll have to go ahead and work it out by hand. But many times it'll work out to be a decimal that your calculator can turn into a fraction, or it'll end up being a nice neat number, and then it's perfectly fine to use your calculator. So here we have the integral of an absolute value. When you're dealing with absolute value, for the most part, you got to look at breaking it into pieces. This one only needs 2 pieces. Sometimes it's going to be 2 or 3 pieces. It all depends upon what causes the inside of your absolute value to be 0. That's where it switches from where the absolute value does something, and that's where it switches from where the absolute value doesn't really do anything. So in this case, what causes the inside to be 0 is just x being 0. So we have to look at what happens between -1 and 0, and then what happens from 0 up to our other bound of 3. So for the most part, we're looking at this area right here for this part, and then we'll be looking at this area over here for the lower part. So what we can do is say, if we try to number between 0 and -1, like -1/2, would the absolute value do something? Yes, it would, because remember, absolute value is going to make it positive, so it's going to take the opposite of what's in there. So in other words, you get the opposite of 2x. Now, if you try to number between 0 and 3, like 1, you put it in here, the inside would be positive, well, absolute value would do nothing, so it'd just be a 2 times an x. So for the most part, we can write this as the integral of the top one, from 0 to back to -1, and then the integral of the bottom one from 0 up to +3. Well, you work this first one out, and you would get a -x² evaluated from -1 to 0. You work this one out, you would just get a normal x² evaluated from 3 to 0. So, sorry about that. You plug in 0 minus what you get when you plug in 1, and do the opposite of that. Make note that it's the opposite of this whole thing. So don't include the negative in with the x when you're plugging stuff in. And then you just have to go ahead and plug in your 3 minus what you get when you plug in 0. So basically we just get 1 plus 9, so we get 10. Now this particular problem, because it is just a nice normal triangle here, and a nice normal triangle here, you could have used geometry to figure it out. But if this is not linear and it was, say, quadratic or cubic, the only way to do it would be to separate it up into different integrals and work each part out. So once again, figure out what causes the inside of your absolute value to be 0, and then it breaks it into those separate integrals, and you have to decide in each area whether it's positive or negative, meaning if the absolute value does anything or doesn't do anything. So now we're going to talk about the mean value theorem. Now we know that this is representing the area underneath our curve. Well, we could say this whole area is a certain number. We could find another rectangle that's got the same width with a given height that would represent that same area. Now, since it would have the same width, this f of c would be your average height. Now, your average height doesn't necessarily mean it's going to be right here in the center. It could be off to the side or the other side, depending upon the particular function you have. But f of c is representing your average height. And it's basically saying that c, whatever you have to put into your function to get that average height, has to occur somewhere between a and b. Could be more than one thing, but it has to occur between there. Could occur multiple times in different locations, but it's going to be between a and b. Now, to find this average height, really you just have to get your f of c on one side by itself, so you can take your b minus a to the other side, and that's what your average value function is saying down here. So f of c is the same thing as y bar, and when you put a bar above a variable like that, that means average or your mean, especially if you've had stats, you should know that. And instead of dividing by our b minus a we have up here, we just multiplied by 1 over b minus a times the original area. So in this case, if we were looking for this value of c up here, there'd be one value of c right here, there'd be one value of c right here, and there'd be one value of c right here if you wanted to find it. Your average height would be from how far up this rectangle goes. That would be your average value of this original integral. So here we're given the mean daily temperature in Athens, Georgia. It's dealing with Fahrenheit, where T is in months. And you should remember from pre-calc, a lot of times our temperature can be modeled by a trig function because it repeats. So we want to find the average temperature from the 15th of September, which is T being 2, to the 15th of December, which is T being 5. Because we're going at T being the months after July 15th. So you'd have to go 1 over the 5 minus the 2. Your 5 being here, your 2 being here, that's how wide our integral is. Then you'd have to integrate your function from that 2 all the way up to 5. Well, you know this in front would just be a 1/3. Now all we have to do is just normal integration. You integrate 61, you get 61t. You integrate cosine, and you get a sine. But remember, we would have to undo our chain rule. The chain rule will give us a pi over a 6 here. So we'd have to undo that, so we'd have a 6 over a pi hanging out. And then you'd want to evaluate your integral from 5 to 2. And that would give us our average temperature. Remember, capital T is your temperature, lowercase t is your time in months. So we could go ahead and put our pi over 6 in front here if we wanted. Now, all we have to do is take 5, plug it in for our t here and here, minus what we get when we take and plug in 2 here and here. Now, this is one that we could work out pretty easily because you're supposed to know that the sine of 5 pi over 6. You're supposed to know the sine of basically pi over 3 because 2 over 6 reduces down to pi over 3. So you could work these out exactly. You could also work this out using your calculator by just typing in this line, and you get approximately 57 degrees.